The third speaker is Professor John Botsis. He's the Honorary Professor of Solids and Structural Mechanics at EPFL. His activities cover experimental mechanics, fracture and fatigue of advanced materials, numerical method, and micromechanics. His talk today is experiments and analysis of delamination of carbon epoxy composites.
Hi, everyone. My name is John Botsis from the EPFL, and the title of my presentation is Analysis of Experiments and Analysis of Delamination of Carbon Epoxy Composites. Here is the outline of my presentation. After a short introduction and motivation, I will give you the objective, then the methods, the experimental part, and then the modeling, which consists of three components: identification of bridging tractions, prediction of the load displacement curves and R curves, and then assessment of the geometry in large-scale bridging. Then, of course, the results and the conclusions. So, as we all know, fiber-reinforced plastics are possessing very high specific properties, and they are commonly used in high-tech applications or structures, like here in aerospace, automotive, naval, energy, and several other infrastructure applications, including sports. Current research in the area is to extend the reliability of composite structures. Now, we all know that due to the difference in elastic properties of the constituent materials and the layer structure, microcracks and damage appears in the interface of the layers or of the laminated structure. Now, these defects generate cracks that develop into delamination that is normally accompanied by large-scale bridging, as we see here on the right, on unidirectional interlaminar, unidirectional intralaminar, cross-ply, and angle-ply layouts. On the right, we see a typical R curve of delamination. We see the energy going from 300 joules per meter square at initiation to about 2000 at steady state of propagation. This is a very important toughening mechanism, the bridging effect, and needs to be really correctly modeled for a better prediction of the behavior of a composite structure. However, this is a strong influence of the geometry. It has a strong influence, it has a geometry dependence, as we may expect. Now, this brings me to the objective. It's characterized traction separation relations in composite materials, in layer composite materials during the lamination under monotonic loads. The approach consists of four parts, as it is shown here. First is generate extensive experimental data, then develop iterative numerical analytical model to evaluate relevant parameters and traction separation relations due to bridging, then implement cohesive zone modeling to predict load history, and finally use computational micromechanics to better understand the controlling parameters of bridging and toughness enhancement. And this brings me to the methods. First, the experimental part, the materials and specimens. We use carbon epoxy, commercially available from Guri. We used a standard profile on autoclave to prepare plates, unidirectional, and then use ASTM standards to prepare DCB specimens of initial crack of 60 millimeters. We performed several tests of specimens with different thicknesses in interlaminar, intralaminar fracture and lamination. The data reduction we followed is a linear case. First, using the compliance calibration, as it is shown here, and this is actually the ASTM standards. And then also we employed a nonlinear data reduction method using the J integral, whose expression is shown here. Theta is the angle of the loading block where the force P applies. It is shown here. Now the angle is measured using digital image correlation, and it is the rotation of these bars as it is shown here. Again, followed by digital image correlation. In this work, we use two distinct testing configurations. The end opening force, as it is shown here, the DCB specimen with the two forces at the ends, and then a pure moment, again, a DCB specimen subjected to pure moments at the ends. Most of the work I will present to you today has been obtained using end opening forces, and towards the end, I'll show you results obtained for using pure moments and then compare them with the end opening forces results. Now, we rely a lot on strain data obtained during the experiment to use them in an inverse identification method to obtain bridge interactions. These strains are obtained using embedded multiplex fiber Bragg grating sensors. There are several points in order to obtain a quasi-continuous strain distribution. The fiber optic on which the fiber Bragg gratings are described is embedded during manufacturing above the lamination plane, as it is shown in this figure. And here what we see is a specimen, a photo of the specimen, and this red line indicating the fiber optic above the delamination plane. During testing, we follow the peak movement of these gratings, as it is shown here. Now, the movement of this peak is delta lambda is proportional to the strain at this location. Here we see a micrograph of a fiber optic integrated within the composite. Here are the results. Now, we have here the intralaminar fracture resistance curves for 4 different thicknesses shown here. Now, notice here that all these have the same initiation, but the R curves differ significantly. As an example, look at the 2 or even 4 millimeter and then the 10 millimeter thickness specimen. So we have a much tougher specimen for the thickest specimen. Here on the left are the strain data for a specimen of 8 millimeters. Now the strains have been acquired at about 20 positions along the delamination direction. Now the dip here is referring to the location, or it's due to the fact that the crack is under the FBG sensor. Now these data are used in a semi-empirical or inverse identification method to obtain tractions. Now here is how we do it. We replace the bridging zone, the bridging fibers, by a continuous stress distribution under bridging zone that we call them bridging tractions. Now we assume or consider these bridging tractions to in this form. It is the product of these two functions, an exponential one and a linear one, with 3 constants, 3 parameters. Now, if I apply some limiting conditions on this expression, I will obtain the bridging traction distribution in this form, where I see the sigma max, which is the maximum stress at the crack tip, the Z max, the length of the bridging zone at steady state, and gamma is a parameter describing the decay of the bridging tractions from the maximum to the 0 value. Now we have built a parametric finite element model and calculate the strains at the location of the fiber Bragg grating sensors. Now we compare the strains between the numerical model and the experiment, and we use an optimization scheme to minimize their difference. Now, out of this minimization, we obtain these distributions of bridging tractions for the 4 different thicknesses, as it is shown here. Now, it's clearly the stresses for the thicker specimen are quite higher as compared to the rest, which again progressively diminish towards the thinnest. Now, what is interesting to note out of this is that the sigma max, the maximum stress at the crack tip, is independent of thickness, and the product of gamma cube times the moment of inertia of the bending arm here is constant, and the Z max is a linear function of the thickness. Those relations are quite important. First of all, they indicate the scaling effects of the process, And also they can be used to obtain tractions for a given thickness, either in between or outside of this range. So what are we going to do with this data now? Now, here are again the same data. Now, this is what we obtained. Now, the same model, the same optimization model, parametric model, gave us the delta crack opening displacements as a function of Z. So I will eliminate now the Z parameter from sigma and delta to obtain a sigma delta, that is to say, tractions in terms of the separation distance delta. And these data now are going to be appended to a cohesive zone model to predict the behavior of this specimen, or the loading response of the specimens. Here you see the cohesive zone modeling. The first part here, the gray zone, refers to the standard one, which corresponds to the process zone ahead of the crack tip, and the GI here is the G initiation. And this is what we have calculated using the model I presented to you earlier for a typical case. Now we can express this behavior or this response with necessary relationships and implement them in a cohesive zone model to predict load displacement curves that are shown here for interlaminar 4 thicknesses and intralaminar 3 thicknesses, 6, 10, and 14. Here again, we go from 2 to 10. So clearly, the cohesive models are in very good agreement with the experiments. Now let's move next to the computational micromechanics. Again, we really need to shed light to the phenomenon of bridging treated so far with the phenomenological approach. Now here, the fiber bundles are approximated by circular cross-sections because of the experiment they are irregular, but the area is the same on each of these fibers. And the fiber itself is modeled as a Timoshenko beam. It is linked to the specimen arms by weak and strong connectors in an embedded cell format. Now the connectors represent the strength and toughness of the interface. Now, the behavior of the weak connector shown here is approximated by a bilinear force opening relationship. Now, the force here, NW, is taken equal to the strength of this composite in a transverse direction. And the green area, which is energy, is taken equal to the energy release rate at initiation of the same material. Now, for the strong connectors, we have multiplied the value of the weak connectors by 1.5 to carry out the simulations, but it could be here, some number slightly different. It won't change the results. So it's just an operational number to carry out the calculations. And here are some results for a given thickness. Now here, the micromechanics model gives us this traction separation. It is the red line. And then compared to the specimen of the same thickness, the traction separation given by the inverse identification method. On the upper right, we see the load displacement response of 3 different thicknesses, three specimens with 3 different thicknesses. And here on the lower left, we see the morphology of the bridging zone developed at different crack lengths and compare to the ones observed experimentally. All we can say here is that the micromechanics model gives a bridging zone geometry and crack position similar to the experimental observations, as it's shown here, and then it predicts very similar traction separation and load displacement curves. This is a very, very nice result because it supports the phenomenological inverse identification method and results we talked about earlier. Now, we want to go a step further in order to understand really the effect of thickness. The micromechanics model indicates a strong interplay between the extent of bridging and specimen thickness. So how can we quantitatively account for it? So as a first attempt, let me show to you here some results. First, again, here the schematic of the bridging zone and the stress distribution. So I define here the delta, the crack opening displacement, and the corresponding crack opening angle phi. Again, phi is given by the first derivative of delta at this point. I can call it crack opening angle, but also the tangent or the derivative of delta at this point. So here are the results where we correlate crack opening angle and the crack opening displacement. Look at this. At very small crack opening displacement, the crack opening angle changes, but it is the same for all 6 thicknesses treated, from 6 to 14. After a certain point, the data diverge, so they are the same, and the thickest specimen and the thinnest specimen differ quite significantly. So this tells us that that bridging has an enormous effect on the crack opening angle. Here again, this very first part corresponds to the bridging zone. I'm sorry, the process zone ahead of the crack tip. So this tells us that indeed, the crack opening angle is very, very important. Now let me go back to the micromechanics and try to justify, at least micromechanically, why the angle is very important, or the angle, or the curvature, or eventually the bending. So here I showed you a mechanism that has been reported in the literature by KAUST back in '93. They considered a fiber bundle under bending between 2 parallel crack faces. This is how they modeled the bridging fibers. Here are the expressions obtained by that model. Again, this is the pressure, the bridging pressure as a function of the angle phi here. Phi, again, is the angle of the between the bundle and the crack face, the moduli, etc. And K here is a weighable parameter. Now, if I just simplify a little bit this expression by assuming phi to be a very small angle and K equal to 1, I will obtain the simplified form where I see here the product of phi and the opening appearing in this pressure. Now, what we believe, though, this is not a mechanism that operates in bridging, especially in bending dominated bridging. So we consider a more realistic mechanism shown here on the right. So we believe that the bending of the arm and the bending of the fiber bundle interact, because both of them take bending. So the extent of damage and propagation depends really on both bending. So as we can see here, crack will advance again depending on the bending of both. So the arm stiffness matters because the fiber bundle in the bridging zone supports bending, and it is affected by the bending of the arm. But how can we really account for this quantitatively? So just a short summary. Now, based on the experimental results in micromechanics and computations, we introduce the local angle as an additional kinematic parameter to accurately model large-scale bridging. That's really what we, if we want to say, postulate and see how we can do this. But again, how to account for it quantitatively? Now, we have not much of a choice but to rely on experimental data. So sigma now will be expressed in terms of delta and phi. The delta in its first derivative. And for that, I will introduce a parameter zeta, which is given by the product, crack opening, and this derivative, again, back on the same schema. Now, I will take now the data that I have at my disposal and see how they look like. From the identification method I employed earlier, I have obtained these 3 different stress opening or traction separation relations for three different thicknesses. The same model gave us the crack opening angle at every point. So I take the crack opening angle and multiply by the corresponding crack opening delta, and establish this parameter z I showed you earlier, and replot the data. So I have here sigma as a function of delta and phi plotted against the delta and the derivative of delta, which is shown here. Now, interestingly, the three sets of data collapsed to a single master curve for this system. Now, for a second system, a glass fiber reinforced polymer, I have here a set of data of five specimens, 5 different thicknesses. I will do the same analysis. Again, from the numerical model, optimization model, I will take the crack openings, multiply the deltas, and then I will obtain this single curve. As you can see here, the results are very, very good, except slightly the specimen with the thinnest specimen shows a small deviation here. It is attributed to the large displacement that we were not considered in the analysis of this test. Here on the lower right, we see a case of a tufted DCB specimen. As you probably know, growing a crack in a tufted specimen is very, very difficult, a long crack. So we normally reinforce it with plexiglass or steel beams. Here what we see is that the curves of a tufted specimen without reinforcement by plexiglass, and the same specimen with a plexiglass reinforced. Now, carrying out the same analysis, we see again a single curve. So this is quite interesting result and demonstrates indeed that the angle plays a significant role in addition to delta to the crack opening. So how do we use them in a predictive, say, model, cohesitism model, to see how the prediction of the low displacement curves looks like? So what we used earlier was the traction separation relation appended to the standard cohesitism model. Here, what I'm going to do, I'm going to use the same first part, which refers to the process zone, and I will attach here the sigma as a function of zeta. Sigma as a function of delta times the crack opening angle. And we have now built a cohesive element that takes rotation, and with this cohesive element, a cohesive modeling approach to predict low displacement curves using this traction separation and angle relationship. It is shown here. And compared with the traction separation that we've already done in the experiments. As you can see here, the response is quite good. Again, justifying that the way the angle has been taken into account is a realistic one. And the last slide of my talk is again on DCB loaded with pure moments and comparing it to the specimens behavior, to the specimen with applied or loaded under end opening forces. So for a single thickness under pure moment, we identify the traction separation relations, and from the also calculated crack opening angle, we constructed the sigma as a function of zeta, which is here the black line. The red line here is the corresponding curve for a specimen loaded under end opening forces. So you see here quite a bit of a difference between these two loading configuration of a DCB. Now, out of this sigma zeta, I can construct sigma delta for 3 different thicknesses, 6, 10, and 14, and go to predict moment angle relations for these specimens. So here they are. Now the middle one is the one we tested, and you see here the result is excellent with the experiment. And then the 2 ones that we predict without any experimental comparison. We haven't done experiments on that, on these two thicknesses, but comparison with what we found in the literature is good and very good, and we believe that the undertaken approach is very sound. And this brings me to the conclusion. To model large-scale bridging, the local COD and the corresponding local arm should be incorporated as additional kinematic parameters, especially the angle, if we want to account for the specimen thickness effect. The proposed approach can be very useful in damage-tolerant design, since it reduces the amount of testing significantly. In fact, you need only a single test, and then you can predict or you can come up with traction separations for any thickness. 3 is that the lamination under end opening forces and pure moment give different traction separation and angle relations. So there is no one test that dominates the other, or there is an advantage of one over the other. So finally, the traction separation relations in LSB large-scale bridging, that is, are not material properties as commonly accepted in the literature. And some acknowledgement. Several individuals contributed to this work throughout the years. The doctors Papas, Canal, Farmat Arstiani, Stutz, Larissa Sorensen, and Professor Chignoni and Alfano, as well as others. And financial support was provided from the Swiss National Science Foundation, EPFL, and industry. At this point, I would also like to thank Professor Gilles Lubinot for his kind invitation to present this work in this workshop, and also for his efforts he and his collaborators have put together to bring this to completion. Thank you.
Thank you, Professor John Botsis, for a very inspiring talk. So Professor Vasilis Kostopoulos, please unmute and ask the questions.
Yanni, really very nice presentation and answer to very many uncertainties that we have faced during the years. My question is how to design using this kind. So what are the intrinsic material properties? Now the intrinsic material properties is the G initiation and the what is and the traction separation load. What is the intrinsic material property that we are going to use for design?
The intrinsic material property is really the cohesive, the G initiation practically in large scale bridging. There's nothing else. I assume it's not a material property, as you saw. It's a geometry dependent, and so the G initiation is practically what you have. So again, if you have a geometry dependent phenomenon, that implies that you are lacking kinematic parameters actually, and this is why the angle was needed to come. Okay, but again, I think the only material parameter I can see now in large scale bridging is the G initiation. And also, it's probably I mean, probably all of you have seen. There's a debate of of the testing. Is this the end opening force or the pure moment? I think this is also something interesting that that came out of this. That indeed those two tests are completely independent, and one cannot use the results from one to predict something on the other test. So,
thank you again.
Okay, thank you, Professor. Thank you, Professor, again for your talk.